Thank you, and thank you all. It's an honor to be here. And so I'm going to talk a little bit about these systems that are the recipient of the changes that Bob talked about, and how important they are in basically in the processes of our basin. Kind of if I was to put a parentheses in our subtitle of this talk, it would be recognizing the importance of our watersheds as part of our fundamental infrastructure, which is sometimes called green infrastructure. So just real quickly, since Bob covered this and gave a great introduction of what some of the things that are happening, on the left is peak flows, and this on the x-axis is recurrence interval in years. On the y-axis is peak flow. And this is data from the UW Climate Impact Center. This is for the NTAD over on the east side of the Cascades, and just showing, again, the big increase in peak flows that these models are predicting, as well as this decrease in our low flows. There's big discussion going on amongst all this right now, and we're facing some big decisions about how we approach it. So, and that includes whether we go down the traditional path that we've done as a society, such as building large water retention facilities, or whether we maybe start considering some other approaches. And that is really the big theme of this talk here. Is recognizing just how nature wants, how it functions with these systems, and how we can re-engage and basically retain more water in our watersheds that would then attenuate lower peak flows downstream, as well as increase base flows in the system. So I'll come back to this site when I show some more examples later in the talk. So legacy impact. So one of the fundamental parts of field of geomorphology has been with regard to landscape evolution is how rivers both cut mountains down and build other areas up. And one of the kind of interesting non-intuitive things is when you think about as you increase precipitation in a system, you're increasing the potential energy, of course, that moves water and thus sediment and erosive capacity. But when you look at global data, as precipitation tends to go up, erosion rates can actually decrease. And I think you all probably can put that together. What's the difference? And that's vegetation. And we've learned a lot more too, just not only on the role forests and vegetation have on the landscape in a watershed, but what happens when that vegetation gets into the channel network. And so this is a little old DFW photo down in the Newaukum Basin, just of a typical log jam. And these, again, were common all over our state, including Eastern Washington. In fact, research in the last couple of decades in New England and many other places is showing it was everywhere. In fact, I think there's some of the folks at Cornell are trying to show that in the Adirondacks, the wood loading is similar to here in the Northwest. On the right is a really neat plot. This is from some work we're doing up in Northeast Washington and on Sullivan Creek, and you see this distinctive hump in the channel profile. And that is associated with a log jam right there. And that traps sediment, lifts up not only the water elevation, but it, of course, is lifting up the entire groundwater table in that stream. It's re-engaging lots of side channel and floodplain habitat. But we're really going to zoom in back to this infrastructure issue of that, the role of this in water storage. So, as one thing we've seen working throughout the West is this pervasive problem of incision. So that's the cutting down, when a channel is basically cutting down through basically not only its alluvium, but potentially right into its bedrock. So there's several things that can lead to incision. One is increases in flow. So we can kind of look at urbanized basins as an example of kind of what climate change might mean, because we know in our urbanized basins we've increased peak flows dramatically. And we typically see a lot of channel incision in these areas. And then utilities and public works folks spend a lot of money then trying to deal with these problems when pipelines are exposed or bridge abutments are undercut. What's kind of interesting is where the extent to we're seeing this. So you can see it downstream of dams, because dams are cutting off sediment supply, so that can lead to channel incision. But we're seeing it in places that don't have dams and don't have development. Throughout a lot of the Olympics, the Cascades, we're seeing channel incision. There's a great Geologic Society of America paper talking about global incision. They done by some colleagues at the University of Washington. In the Attenuate Basin, they looked at not only in the last 100 years did the river cut through 2 meters of alluvium, it's cut 2 meters into the underlying bedrock. So that, of course, totally has not only had a huge effect on habitat, but it has all the water that used to be stored in that system is just flushing right out. So the other changes we've done that can impact this is, which is more pertains to our larger systems, is channelization. So when we reconstruct rivers, this is an example down in the Shales Basin, what many of our rivers kind of looked like when the first Europeans showed up. They were very different. The kind of underlying message would be there was a lot more channel length. Even ones that still retain some of their sinuosity, we know that they had a lot more perennial anabranches or secondary channels in the floodplain. That's just kind of a schematic of showing that kind of difference that could exist in a system and the engagement of these channels. This is just a little photo of where some simple wood additions to Ellsworth Creek down in southwest Washington brought up water table and engaged these channels immediately. So I'm going to show a couple figures. Bob showed a great one just as far as when that last hydrograph he showed of the projected changes in 2015 data. But this is on the Skagit. And what I want to point out here is, so here's a hydrograph 1995, of date, time on the x-axis, discharge on the y-axis. And the red curve is peak flow in concrete. And this blue is the peak flow downstream. So even though there's a big increase in drainage area between these two gauges, the peak's actually dropping down. And that's because of the effect of the floodplain and as far as attenuating or moderating that peak. This is a more kind of dramatic illustration, and this is actual real data from Vermont when it got hit by Hurricane Irene. So again, the upstream gauge here in Rutland, Vermont, where they experienced millions of dollars of damage. Here in the red, see the red, and then the black curve here, or in the blue text, is down in Middlebury. So that's more than a doubling of the drainage area. So you would expect, again, as you're going lower in the system, that you're accumulating flow in especially a big precipitation event. But you can look at a very different, there's about more than 50% reduction in the peak, and you could see that water just being spread out and moderated and a much broader hydrograph. So the big difference here, or the key kind of information you're not seeing, is that the Nature Conservancy worked with locals and some of the farmers in the Otter Creek Valley and created a big preserve. And basically where they had a broad forested floodplain, that was able to attenuate that peak flow. So kind of reiterating some of this, that we can use these kind of simple regime equations just that are pretty intuitive of just how increases in water are going to have geomorphic responses or increases in flow that change your channel geometry, and then the consequences that can have to your system as far as becoming more, increasing conveyance through the channel network, reducing roughness, and so on. You also, when you look at these impacts, then you can start to have additional impacts on ecologic attributes as far as, say, shade and ultimately water temperature. There's some great work that's come out of Northeast Oregon looking at some of this effects and how these channel geometry changes, as well as, of course, the riparian vegetation can affect channel temperature. So the key on some of the work we're doing, and I want to acknowledge one of the key people in this work is Susan Dickerson Lang, who's here today, that's been working closely on this, and also Chelan County, who's been supporting some of our work on this, but is looking at this whole issue of water storage and how it can ultimately affect these hydrographs. So the basic premise here is that you have an alluvial valley in your network, so this can extend up into headwater channels. And when you have incision, so if you have had a legacy impact of intensive forest clearing, or you have wood removal, and the wood is becoming recognized, again, a lot more than just a habitat issue. So kind of what wood does, it dissipates energy. So that the shear stress that's available to move sediment becomes much more effective. I mean, what's actual available goes up as you reduce wood, because the wood is partitioning or consuming some of that energy. And so that then results in more ability to move sediment, and your channel cuts down. And so that's happened in tens of thousands of miles of stream throughout the state. The other thing to recognize too is that the water storage, we can all understand when a beaver comes in and you can actually see that surface water increase, but you're also increasing the water table in the alluvial reservoir or the alluvial sediments within the basin. So again, depending on the porosity and the geologic material there, you can get close to 30% of that volume can be water. So here's another hydrograph, so time and stream flow, showing again the effects of different after stream restoration here. And there's been work out of some of the high elevation meadows of the Sierra have kind of pioneered some of this work on the importance of water storage and how channel incision has impacted these systems. So I'll go through some examples. This is the Nooksack, South Fork Nooksack project the Lumbee Nation did, and I'm really proud of. This part of the river had incised on the order of 3 meters, was moving boulders of a meter or more. It was down in the glacial sediments. And again, we basically put material back into the channel and raised up the water table and engaged all sorts of floodplain that hadn't seen water in a long time. So I'll wrap up here. This is over on the East Cascades, an entrenched little section of creek that on Toppenish Creek you could see low flow well down inside the banks. I'm going to show the same site, slightly different perspective, and a similar flow that is now water all over the place. And our lead on this project, Deb Stewart, is here if anybody wants to talk more too about that work we've done over there. Again, getting really positive response even from the ranchers and cattlemen over there as they see the water table come up and the importance of that storage. So here's kind of we've done some theoretical and hypothetical work of what this can do, even going up into low water, small channels, of what restoration can start to do as far as storage, water storage. And so as you add these up, we take this seriously the same way we do with our water supply infrastructure. We could potentially be storing hundreds of thousands of acre feet, even starting to get into the millions of acre feet, if we put our watersheds back together. And so, in other words, all that hundreds of thousands of acre feet of water, what I'm saying is that water's gone now. It's leaving the system, and we're not getting that benefit, particularly in the during our dry parts of the season. Again, just an example of where with all that wood in Sullivan Creek, where it is, and holding that grade. This is where I started out the Clay Ellen project, showing during a relatively moderate flow the floodplain engagement. So, anyways, thank you all so much. Hope I didn't go too far over. And if there's any questions.
Yeah, I would like to ask, you bring up an interesting question, because looking at the Nooksack, and I've lived here all my life, and canoeing the Nooksack, a lot of people, when they look at the Nooksack and they see the width of it, they say, oh, width equals depth. Well, that's not true. In a lot of places, with all the settlement and the erosion stuff, the river's quite shallow. In fact, maybe into 4 feet or whatever, a person can walk across it. Has any studies been done about this, about, I'm going to use an unpopular word, but dredging or doing some? Because the shallow water is not good for the salmon. And I don't know if every mile or quarter mile or half mile, I don't understand it well, but if we created a place for the salmon to get to where it's really deep, it's trees growing, where they can get a break, and then they hit it up the river in that shallow. I don't know. I'm just throwing something out.
Sure, it's a great question, and I think later today Mike Modlin may talk to some of this. So when there's, in geomorphology, a term channel evolution model of kind of what you could expect a channel to, you expect it to change under certain when you change some input parameter. So the whole story of incision is, so if you do something like increase peak flows or remove the wood, the first thing that'll happen is it'll cut down. And this is the geomorphic channel. So don't think of it necessarily as water depth, but just the channel itself. So then the next stage is it will widen. And so if you then get a wider channel, during the low flow periods, so if you're also decreasing your low flow, you could see you're now going to immediately have much shallower water because you've got a wider channel. And so the other thing that happens, and I think restoration's doing a really good job of, is you put structure back into the channel and you get riparian reforestation to help stabilize banks and wood in the channel. It helps to not only increase pool frequency and depth in those locations, but help better define a low flow channel. But what you're describing is kind of a common scenario for what has happened to a lot of our rivers.
Just a quick one. You mentioned at the beginning a sort of subtitle. Would you entertain a different title, just Jams Before Dams?
That would be great. I mean, most of you know my background and passion for wood, which makes me sometimes feel like there's a conflict of interest. But I do kind of feel the message needs to get out there of truly what has happened to our systems, and I think the science is all starting to back this up. That and incision is a really insidious thing. The Missouri, despite all the dams, has incised almost 15 to 20 feet, and what it's done is it's come back to haunt them because now power plant intakes, irrigation intakes are all up here, bridges are threatened, and it becomes $1 billion problem.
Hey, Tim. So I'm wondering about storage and cost, comparing dams versus log jams. And have you kind of looked at that?
We have started to look at that, and our preliminary estimates are that a massive restoration program that recognizes these benefits beyond, and of course, fish would be a secondary beneficiary of this, but would be that at least half the cost of dams to potentially much less. And then, of course, with all sorts of benefits versus the negatives we've learned that come along with dams. Thank you. All right.